This is not just a technical roadmap. It is the screenplay of a quiet revolution. It is the story of how one company, starting from the shadows of its own past and the long shadow of its competitors, decided to stop repurposing borrowed tools and begin forging the dedicated infrastructure required to build the future of artificial intelligence. This narrative is about the evolution of AMD's Radiant Instinct, a decade-long climb from a humble graphics card, adapted for the data center, to the core engine of the world's first Exascale supercomputers. We are going behind the curtain, chapter by chapter, to explore the architectural shifts, the engineering breakthroughs, and the decisive moments that transformed a side project into the cornerstone of modern high-performance computing. Every epic journey starts with a simple, sometimes awkward, first step. For the Radiant Instinct lineage, this initial chapter, the transitional era, is defined by a bold yet practical necessity. AMD's initial attempt to push general-purpose graphics silicon into the data center before compute and graphics were split into different product lines. Imagine a dedicated team of engineers staring at a high-performance sports car, a consumer GPU, and being asked to adapt it to haul cargo across a digital continent. They knew the destination was the future of compute, but the vehicle they were given was designed for rendering video games. The MI6 and MI8 were the stepping stones of this period. They represent the ultimate pragmatism. These were passive server cards built from consumer GPU chips, stripped of their flashy graphics outputs, and repurposed for the quieter, more intense world of the rack. They were focused on inference and modest compute. Their greatest limitation, however, was a profound one. They offered no acceleration for reduced precision math. This is critical. In the nascent world of AI, the ability to calculate with less precision, for example, half-precision floating point, is the key to both speed and power efficiency. Without it, these early accelerators were reliable workhorses, but they were confined to the slower lane of full-precision computation. They were the first foray, the proof of concept that said, yes, our silicon belongs here, even if they weren't fully optimized for the task. They were like the early telegraph, a clear message sent, but in a deliberate, measured pace. Then came the first true breakthrough, the first sign of real dedication, the MI25. This card delivered the first meaningful leap with Vega 10. This was no mere repurposing. This was the moment the silicon began to be tuned. The MI25 introduced fast FP16 execution. Think of FP16, half precision, as the Rosetta Stone for modern machine learning. It allows the card to process data with half the bits, immediately doubling the theoretical throughput and drastically improving power efficiency for AI tasks like training neural networks. This single feature, coupled with higher power envelopes, fundamentally established the foundation for real machine learning capability inside the rack. It was the moment the humble cargo hauler received its first specialized engine upgrade. The MI25 proved that AMD was not just visiting the data center. They were moving in. This entire period is a masterclass in starting with what you have, learning on the job, and then pivoting to dedication. It shows that initial success doesn't always come from a revolutionary new design, but from identifying the single most limiting factor, like the lack of FP16, and solving it with focused engineering. The MI6 and MI8 were the prologue. The MI25 was the first sentence of the real story. If the first act was about proving capability, the second is about professionalization and commitment. The narrative shifts from adapting graphics-first silicon to AMD's first real attempt at data center-first GPUs. This is a philosophical and economic pivot. Resources, design cycles, and manufacturing choices are now prioritized for the data center's unique, unforgiving demands. The stars of this chapter are the Mi-50 and Mi-60, built on TSMC's advanced 7 nanometers process. This manufacturing leap is the physical manifestation of the shift in focus. Moving to a smaller process node isn't just a number. It means immediate, significant gains in efficiency. For the data center, where every watt of power costs money and every degree of heat threatens uptime, efficiency is king. Mi-50 and Mi-60 were designed for efficient thermals right from the start, a necessity for the tightly packed, hot environments of server racks. But the commitment ran deeper than just thermal efficiency. These accelerators added structural integrity to the computation itself. They delivered significantly higher floating point throughput, meaning they could perform more raw calculations per second, direct, measurable leap in performance over their predecessors. More importantly, they introduced ECC, error-correcting code, memory reliability. ECC is the digital equivalent of a dedicated quality control team. It detects and corrects data corruption that can occur from heat, cosmic rays, or voltage fluctuations, issues that are rare in a gaming PC but unacceptable in a mission-critical server running a trillion-dollar financial model or high-stakes scientific simulation. ECC is what transforms a fast chip into a trustworthy foundation. Finally, they integrated PCIe 4.0. This seemingly mundane specification is crucial. It's the highway that feeds data to the GPU. With the rise of high-throughput compute, the GPU was constantly being starved of data by the previous generation of PCIe. PCIe 4.0 helped to reduce these data-feeding bottlenecks, ensuring the powerful new silicon wasn't waiting idle for its next instruction set. The Mi-50 and Mi-60 thus represent a closure of a critical gap. They closed the gap between graphics-derived hardware and purpose-built compute GPUs. They possess the speed, the thermal discipline, and the reliability demanded by serious enterprise. However, even with this monumental step forward, a significant challenge remained. They still lacked dedicated tensor engines. This meant that while they were powerful, versatile machines, they were inherently limiting deep learning acceleration compared to NVIDIA at the time. They were now world-class professional tools, but they hadn't yet been weaponized with the specialist AI cores that would define the next generation of machine learning hardware. It's the story of a champion boxer who has mastered every punch but has not yet developed the specialized signature move that defines his legend. The foundation was rock solid, but the specialization was still to come. This is the moment of architectural and philosophical divorce. Act 3 marks a decisive turn, the breakaway moment where the legacy of graphics is intentionally and cleanly severed. The engineers drew a line in the sand and declared a new identity. The next chapter is defined by the unveiling of CDNA compute DNA. This wasn't an evolution of an old architecture. It was a pure compute lineage, a manifesto carved in silicon. ND drops graphics logic entirely. This may seem subtle, but it's a profound declaration. Graphics logic components dedicated to rendering triangles, textures, and shading for displays consumes valuable transistor space and power that could be otherwise dedicated to calculation. By purging it, AMD freed the chip to be a singular, unrelenting focus on pure computation. The flagship of this new era is the MI100, and it is defined by a series of foundational additions that irrevocably changed the game. The most significant is the introduction of matrix cores. If the Mi-25's FP16 was the Rosetta Stone of AI, the matrix core is the dedicated high-speed press for printing the language of deep learning. These are the dedicated tensor engines that were conspicuously absent in the previous generation. They are specialized units built only to perform the complex, repetitive matrix multiplications that define neural network training. This single addition is the turning point where AMD stops repurposing gaming GPUs and begins creating dedicated neural network hardware capable of modern training workloads. The Mi-100 further refined its specialized approach by embracing multiple mixed precision formats and adopting unified high-bandwidth memory, HBM. Mixed precision allows the chip to intelligently use the precision level required for each step of the calculation, maximizing both speed and accuracy. HBM, stacked vertically on the chip, provides unprecedented memory bandwidth, which is the lifeblood of training massive AI models. Finally, the Infinity Fabric multi-GPU scaling was introduced as a core design element. Infinity Fabric is the high-speed communication network that allows multiple MI100 chips to talk to each other so seamlessly and quickly that they can function as a single, massive computational entity. This is vital for the largest training runs, which require the cooperative power of hundreds or thousands of accelerators. The MI100 represents a clean slate. It is the moment the company declared its vision, an architecture purpose-built for the AI era. It's the technological equivalent of an inventor finally patenting their own revolutionary engine after years of modifying existing ones. It is a story of focus, where the decision to remove graphics logic was just as important as the decision to add matrix cores. If CDNA was the Declaration of Independence, CDNA 2 is the deployment of the full naval fleet. This act takes the specialized compute lineage established by the MI100 and scales it to unimaginable heights, transforming the Instinct brand from an experiment to a cornerstone. The story escalates dramatically with the introduction of the MI200 series, MI210, MI250, and MI250X. The key innovation here is the adoption of a chiplet-based GPU design. Before this, a GPU was typically a single, massive piece of silicon, a monolithic die. The chiplet approach involves breaking that massive chip into several smaller, specialized dies and connecting them together using the high-speed Infinity fabric. Why is this a revolutionary act? Manufacturing a single huge chip is extremely difficult and prone to defects, which results in low yield and high cost. By using chiplets, AMD could manufacture multiple compute dies more efficiently and then integrate them together. This immediately delivered massive leaps in FP16, FP64, and matrix throughput. It was like discovering a way to manufacture flawless components separately, and then assembling them into a machine far grander than any single component could be. The MI200 series was not just a theoretical improvement. It was designed for a monumental task. These accelerators drove the Frontier supercomputer, a machine of historic significance. Frontier became humanity's first officially recognized exascale machine. Exascale means the machine can perform 1 quintillion 1018 floating point operations per second. That is a performance level that was once the domain of science fiction, reserved for tracking the formation of the universe or simulating complex, planet-scale climate models. Frontier's success, powered by the MI200, cemented AMD as a major force in high-performance computing. This machine was the ultimate validator of the CDNA architecture and the chiplet design. The MI200 series moved the Instinct brand from being a promising contender to a verified global leader. The shift from a repurposed server card, MI6, to the engine of the world's most powerful machine, AN250X, is the defining narrative arc of this entire journey. It is a perfect illustration of how commitment to a focused architectural vision, CDNA, can deliver results on a truly unprecedented scale. Having proven the power of dedicated AI silicon, MI100, and the scalability of chiplets, MI200, Act V turns to a new, even more profound form of unification, the death of the traditional server boundary. This chapter introduces the concept of the heterogeneous superchip. The protagonist here is the MI300A. This device represents a fundamental rethinking of server design, challenging the decades-old separation of the central processing unit, CPU, and the graphical processing unit, GPU, on a motherboard. This is the creation of a unified compute package. In the traditional system, the CPU and GPU have their own segregated memory, and data must be physically copied back and forth across the PCIe bus, a time-consuming bottleneck, like two separate libraries having to mail books back and forth to share resources. The MI300A eliminates this barrier. The memory becomes fully coherent. This means the CPU and the GPU can access the exact same memory space instantly, without the need for copying or synchronization overhead. This architectural shift enables large simulations and training jobs to run on one integrated device with unparalleled efficiency. For scientists and AI researchers running massive, complex codes like atmospheric modeling, astrophysics simulations, or vast material science studies, the coherence eliminates one of the most frustrating performance hurdles. It's like giving the brain, CPU, and the muscle, GPU, a shared instantaneous consciousness. This new architecture is more than just a component. It is a system-level philosophy, and its power is validated by its role in powering the El Capitan supercomputer. El Capitan is designed to carry the torch lit by Frontier, continuing to push the limits of exascale computing, particularly in areas like nuclear stockpile stewardship and national security research. The MI300A is the embodiment of integration, showing that sometimes the most powerful innovation isn't more speed, but less friction between components. The MI300E Act V was about unification for supercomputing science. Act V, featuring the MI300X, is about maximization for the AI industry's hottest new requirement: large language models, LLMs, and transformer models. The focus returns sharply to standalone, pure GPU acceleration, but with a previously unattainable level of memory density. The AI landscape shifted dramatically with the rise of transformer models. These models, like the engines behind the generative AI revolution, are not just compute-hungry. They are memory-hungry. They require vast amounts of memory, RAM, to hold the model's weights, the input tokens, and the intermediate calculations. The MI300X was built specifically for this rising demand. It achieves this through two staggering numbers. It maximizes memory capacity and bandwidth. With 192 gigabytes of HBM3 and over 5 terabytes per second of throughput. Imagine a traditional computer having to swap data between a small desk, the GPU's memory, and a distant file cabinet, the system's main memory. For a giant LLM, the MI300X provides an inner library, 192 gigabytes HBM3, so vast and so fast, 5 terabytes per second, that the model can hold nearly all the necessary knowledge right where it is needed, eliminating bottlenecks and allowing for unprecedented model scale. The computational specialization is also fine-tuned. The execution of FP8, BF16, and INT8 is explicitly targeted at large language model training. These ultra-low precision formats allow the model to maintain accuracy while drastically reducing the required computation and memory footprint, making trillion-parameter models feasible. The physical deployment model of the MI300X completes the picture. It enables HGPU nodes linked through Infinity Fabric, creating high-density AI systems that compete directly with NVIDIA's top-tier platforms. This is the company making its definitive play for the commercial AI cloud market, building the most dense, memory-rich platform possible to serve the companies training the next generation of digital intelligence. The MI300X is a story of scale, specialization, and direct competition in the most demanding theater of the tech industry. In the fiercely competitive breakneck speed world of AI, time is the ultimate currency. Act 7, centered on the MI325X, highlights a critical strategic pivot, the shift to a rapid iteration cadence. It is the story of seizing an opportunity for immediate advantage without waiting for a full, ground-up architectural overhaul. The MI325X is described as a high-capacity CDNA 3 refresh. It takes the powerful foundation laid by the MI300X and pushes its memory capabilities to a new extreme. The accelerator upgrades MI300X with 256 gigabytes of HBM3E. The E in HBM3E signifies extended or enhanced, meaning not only is the capacity higher, 1/4 terabyte on a single card, but the speed is also inherently faster than its predecessor. This increase to 256 gigabytes of HBM3E is a direct response to the insatiable appetite of the most complex, trillion-parameter LLMs. Larger models require larger memory to hold their state during training. By offering 256 gigabytes, AMD enables larger models to be trained on fewer devices, simultaneously reducing system complexity and cost. Furthermore, the refresh includes improved interconnect tuning. This means the Infinity Fabric communication between the chips is optimized, leading to reduced communication overhead and more efficient multi-node scaling across a cluster. This rapid iteration has immediate, tangible consequences. AI cloud providers adopt it for training and fine-tuning modern LLMs. This adoption is a validation of the strategy. Instead of waiting 2 years for a new CDNA4 architecture, the MI325X solidifies AMD's position in extreme capacity accelerators now. It demonstrates agility and responsiveness, showing the market that the company can provide necessary, incremental leaps exactly when they are needed most. This act is a lesson in the power of optimization, the continuous, aggressive refinement of an already excellent product. The narrative now advances beyond the present, into the anticipated future. The forthcoming stars of this act are the MI350X and MI355X, defining the next generation of performance. CDNA4 takes the extreme memory focus of the previous generation and extends it further. It boosts memory to 288 gigabytes of HBM3E and expands the theoretical bandwidth to roughly 8 terabytes per second. This massive increase in both capacity and the speed at which data can be accessed signals the hardware is being designed for the inevitable. Models that continue to grow in size and complexity, demanding resources that today's systems can barely fathom. But the most fascinating innovation is the focus on new ultra-low precision. Formats like MXFP6 and MXFP4, these are not just smaller numbers. They are a philosophical commitment to AI efficiency. Traditional precision FP32 is often overkill for the actual training of a neural network. By using MXP6, for example, a custom 6-bit format, and MXFP4, 4-bit, the MI350 family can perform computations with incredible efficiency and speed, directly targeting transformer workloads with unprecedented performance per watt. This is the hardware learning to speak the language of AI with the fewest possible syllables, maximizing throughput. To handle the scale this enables, the architecture is hardened and optimized. Enhanced compute units, cache structures, and scheduling are all fine-tuned. This is not about single-card performance. It's about preparing these accelerators for multi-thousand GPU clusters and trillion-parameter model training. The MI350 is the infrastructure required for the first generation of AI that will truly understand and generate human language at a mastery level, trained on datasets so large they encompass a significant portion of human knowledge. CDNA4 is the foundation for the next decade of AI breakthroughs. The story must zoom out from the individual chip to the total environment. Act 9 depicts the culmination of the architectural journey, a shift from selling single accelerators to delivering complete AI infrastructure. This chapter describes the modern instinct deployment model. The unit of compute is no longer the card. It is the liquid-cooled rack filled with MI325X and MI355X GPUs. The move to liquid cooling is a necessity for achieving the density required to pack hundreds of terabytes of HBM and petaflops of FP8, FP4 compute into a single server unit. The genius of this infrastructure is the software and networking layer. ROCm software, the AMD open-source platform, and the specialized Infinity Fabric networking work in concert to create a fully unified training fabric. This fabric is the high-speed nervous system that ensures all the components communicate instantly. The low-precision math pipelines from the individual chips are integrated seamlessly into this system. The end result is an infrastructure that allows massive distributed training as though the entire cluster were a single machine. The programmer doesn't have to wrestle with the complexity of managing thousands of individual devices. They write code for a single, colossal entity. This is a profound simplification of the AI training challenge. It's the difference between managing a chorus of individual singers and having a fully synchronized, perfect choir with a single consciousness. This rack-scale vision demonstrates that the future of compute is not just about the silicon, but about the seamless integration of cooling, networking, and software, the ecosystem that allows a trillion-parameter model to finally come to life. The final act is the closing of the loop, a look toward the unfolding horizon of 2026 and beyond. This is the story of sustaining revolution, the ongoing commitment to innovation that ensures the architectural journey is perpetual. The closing chapter of this narrative is defined by the promise of the MI400 series. This series is expected to define the next generation of performance and integration. But the most visionary aspect lies in the continued evolution of the chiplet approach. The MI400 is expected to use even more flexible chiplet arrangements mixing GPU, CPU, and specialized accelerators. This is the ultimate realization of heterogeneity. Future accelerators will be fully modular, allowing AMD to snap together a GPU compute tile, a dedicated Zen CPU tile, and perhaps a tile specialized entirely for, say, quantum error correction or a specific AI function, like spiking neural networks. This bespoke customization will allow systems to be perfectly tuned for highly specific workloads. The underlying philosophy is that CDNA Next continues the shift toward AI efficiency optimization, cluster scaling, and software-integrated compute fabrics. This final stage represents AMD's full transformation into an AI compute infrastructure leader. They began by adapting a graphics chip. They will end as the architects of a fully modular, Exascale-ready computational universe. The journey is one of profound growth, from tentative steps, MI6, to a bold, self-assured roadmap for the future, MI400. The story of the Radiant Instinct and CDNA architecture is not just a hardware success story. It is a profound lesson in three core principles that apply to innovation, business, and personal growth. 1. The power of dedication over adaptation. The company started by adapting what they had, consumer GPUs. True success, however, only came when they made the ruthless decision to drop graphics logic entirely, A100, CDNA. This teaches us that sometimes in life or in business, the path to revolution is not by improving an old tool, but by clearing the slate and creating a new one purpose-built for the goal. The greatest constraint is often the one we are unwilling to abandon. 2. The wisdom of modularity, chiplets. The transition to the chiplet design, MI200, was a masterstroke of engineering, overcoming the manufacturing limits of a monolithic design. It shows that by breaking a massive, complex goal into smaller, high-quality, interconnected modules, you can achieve a scale and resilience that was previously impossible. In your own massive projects, are you trying to build one single, fragile monolith? Or are you building a resilient system of high-quality, interconnected chiplets? 3. Coherence and unity is the ultimate speed. The MI300A's greatest innovation was full memory coherence, making the CPU and GPU share one mind. We often talk about individual speed, but this story shows that the true bottleneck is often the friction between components. When data, goals, or resources are shared instantly and seamlessly, the collective power is unleashed. Seek coherence in your own teams and relationships. Eliminate the friction of miscommunication and watch your collective power exceed the sum of your parts. This entire journey is a testament to the fact that revolutions are often quiet, architectural, and sustained over years, not moments. They require vision, tenacity, and the courage to build something new, even if it means leaving behind a successful past. What are the matrix cores you need to adopt right now to accelerate your own goals? And what graphics logic do you need to ruthlessly eliminate for the sake of pure, focused efficiency? Thank you so much for joining me on this deep dive today. Wishing you all the very best of health and happiness. And if you found this journey as fascinating as I did, please consider hitting that subscribe button and ringing the bell so you don't miss our next adventure into the heart of technology.